How about that? Yes. Okay. All right. Welcome, everybody. Sorry about the long setup time. Does anyone know who the model was for the DerbyCon logo? Do you know who it was? It looks kind of like Antoine Dodson, just a little, but in a ponytail. Okay. All right. Well, anyway, for those who don't know me, I got a good introduction, so I guess we don't really even need this slide. But so a little overview. I'll go through some background about Java, talk about some of the things that get in the way when you try to write exploits for native code vulnerabilities in the JVM. Talk about some tricks to get around those, and then just do a quick demo and wrap up with my complete hatred for Java. If you can't see, it says there on the notepad, people and things that I hate. I thought it was fitting. So the motivation here is to give you guys some information about JRE and, like I said, the hurdles and tell you about future work. So why Java? You can see here 3 billion self-proclaimed devices from Oracle. Just a few devices, I guess, right? Who here doesn't have something that runs Java? I guess that's nobody. Who here has something that runs Java? Okay, just checking. So it's cross-platform, as you all know, but this talk's going to focus on just Windows. OS X actually is not here on this list, but it up until Lion, it shipped installed by default, turned on by default. In Lion, they changed it so that it doesn't install by default, and if you install it from the command line, it doesn't even enable the browser plugin. So they're really like taking an aggressive stance. I guess they hate Flash too. So 6 is all I really covered, even though 7's out. 7 was released, for those of you who don't know, is with a major issue where it optimized loops when it was doing JIT compiling, and which actually completely failed and caused it to crash anytime it optimized the loop. So they recommend you can use it just as long as your program doesn't have any loops in it. Yeah. So that's part of why I'm not covering it. Also, the adoption isn't really going to happen anytime soon. Like, it's not being offered as an update because it sucks, it's broken. But, it does have all the ASLR and stuff, so great. 6 had 27 updates. It's on, I think they're working on 29. There's a pre-release for 29 out now. But 5 years it's been out. Oh, by the way, this picture actually came from the blog post when they released 6. They were like, yay. But I thought it fit better in here for some reason. So overall, over 100 CVs. I think if you search the CV database, it's something like 147 CVEs just for JRE 6 alone. In 73% of exploit kits, it's targeted. They have at least one exploit. I think 40% of those, not 40% of the 73, but 40% of the total had more than one Java exploit in it. So, bad guys are totally like, you got Java. Yeah, we got shells. Metasploit has 10 exploits. I wrote 2 of them, or no, maybe 4 of them. But only 3 of them involve memory corruption. And of course, everyone loves Java signed applet, the wonderful meatware attack. 4 are Windows specific, and most of them are multi-platform. The 2 memory corruption ones that I wrote, I think, should work on any platform with some love. Anyway, so I got this awesome picture out of this wonderful white paper that I recommend anybody who wants to mess with Java read. It shows just how big Java is and how much bullshit's inside. Everything in between the lines is JRE. Everything above is basically just a documentation. Oh, and the language at the top, which can't be neglected. So it has a huge attack surface. A lot of people, until you really dive into it, you don't realize how big it is with the browser plugin, which is automatically installed. Actually, it used to be that you could pass a command line option to the installer to not install the plugin. But as of like update 10, they're like, no, everyone needs the plugin for all browsers all the time. So anyway, with Applets, it's a very interesting attack surface, and it gets much larger than sort of WebStart or any of the other ways that you can trigger Java. Live Connect is their way to communicate with JavaScript back and forth. Yeah, so attackers use applets most of the time, and the reason is because all the Java code that it goes into an applet is pretty much written by the attacker. And not only that, but applets are usually packaged into a jar, and jar files are zips, so you can put gigantic files of whatever you want, and it compresses down really nicely. So that it can make some exploits much easier to accomplish. So with applets, there's two kinds basically. There's signed applets and there's unsigned applets. Signed applets, which is what the Java signed applet uses, of course, those run with full privileges. They always require a prompt to be accepted, unless the user has like whitelisted them. When the dialog comes up, I don't have a screenshot, but has a checkbox and it says, always trust this publisher. And if you do that, then you won't get any more prompts, and I wouldn't recommend that. But untrusted applets, they run without any prompting whatsoever. Generally, you'll see, a splash dialog or some silly animation with, I don't know, with coffee cup and spinner. But the limitation is that they're subject to the sandbox, right? And I put this in quotes because it's not really a real sandbox like the way, modern exploitation people think of a sandbox when they think of like Chrome sandbox or the sandbox that Office uses or Adobe Reader. So this sandbox was made in the 90s, and that's when they coined the term. And basically it's just a whole bunch of if statements in the code to say like, hey, are we supposed to be doing this? Maybe not. The security manager is what controls that. So from applets, despite you writing Java code, underneath, it's all native code underneath. So they have a ton of libraries for images and sounds and audio compressors and a whole bunch of stuff, really. And that's all in native code, and it's all reachable through core Java classes. You can pass like, for example, you can pass like a sound file that's in your jar and tell Java to load it right from the jar, and it'll process it with the native library. Here's a little picture that I got out of that an older copy of the same white paper talks about how Java code is compiled and then into bytecode. And then once the JVM will run the Java application or applet, it'll then compile that into it'll just in time compile that into native code. Even if it doesn't, there's some cases where it doesn't JIT. If it doesn't JIT, then it will still be native code underneath that's interpreting the bytecode. So a little slide here on the process architecture. Can you guys see the screenshot okay? So as of update 10, they decided for reliability reasons, which I guess that means it crashes too much. So they decided to run it as an external process to the browser. So you can see all three browsers are represented here. And what it does is it launches the JP2 launcher, which is just a stub that takes some stuff and then passes it to the Java executable. But the plugin fires that off, and the plugin loads in the actual browser address space still. So when they did this, they made it so you couldn't use you couldn't use a regular browser heap spray that everyone was using back then to kind of like prime the memory for native code exploitation in Java. The interesting thing here also from this picture you can see is JP2 launcher and java.exe do not have dep or ASLR. And this is the latest update, so I know there was some confusion with a friend of mine. We thought, they opted in and stuff, but they totally do not opt in still. Let me see. They also added some stuff in update 10, which is really interesting for exploitation, and that's they added the ability for the guy who's making the applet to pass all kinds of wonderful arguments down into Java, like, oh, maybe we can, the default heap size is like 50 megs or something. You can just go ahead and set that to a gigabyte or whatever you think Java might need. Or you can say, oh, well, I don't really like the latest version of Java. I'd like to use the older version. So one of the big things about security with Java, and this is pretty widespread, everyone really knows about this, is they ship this DLL, and it's the same version across all 27 updates. So I guess that means they've been using .NET 2003 compiler for 5 years. This thing loads in all the components of Java. It loads in the browser plugin. It loads in the application itself. It even loads in the JP2 launcher thing, which I don't know what it needs it for, but I guess for the runtime, right? But anyway, there's a bunch of public ROP chains that target this DLL. There's one that was released by Corland, and then White Phosphorus released theirs, and then Corland released a better one, and another better one, and another better one. So I have one too, somewhere. But no, it's not better. I made it manually, you know. It takes forever.
6 hours.
Sometimes. So in Java, it's a stack-based virtual machine. So that means, you know, they use the stack to pass things to other functions, and you know, they really stay close to the way hardware works with that. They put a bunch of crazy metadata, and they have like Java objects, which they pass around in the stack as well, but it's more like a pointer to a structure with all kinds of pointers to more structures, and it gets kind of crazy. But I'll talk more about the Java object heap in a second. The native heap is implemented in that C runtime library, and it's basically just a wrapper around heap alloc. So that means that, you know, if you're on Windows 7 and you trigger like a whole bunch of allocations of a certain size, it'll turn on LFH, and you'll get ASLR from that heap, and you know, all kinds of really annoying things that you don't like. But the Java object heap is different. The Java object heap is garbage collected, so that means, you know, if you allocate a whole bunch of objects, the developer doesn't have to care at all about those objects. They'll just go away whenever they needs memory. It actually is implemented in virtual alloc. Like the way that they do it, they allocate a huge like chunk of memory, and then they just divvy it up themselves. I think actually in a recent update, and they didn't mention this as an actual, you know, because Oracle doesn't say shit about the vulns. They're just like, there's vulns, fix them. You know, we fixed them, maybe. But there was one that I noticed. It was a very strange change, and I don't actually have a screenshot, but it seemed like they were fixing an integer overflow in the actual allocator itself. Very disturbing. So up until update 18, this giant memory segment was read, write, and executable. So this information was published by Mark Dowd and Alexander Soderov in their bypassing browser protections paper in 2008. I'm not really sure why, but this thing loads at the same address all the time. So we have an RWX memory segment filled with stuff we control, because we control the Java object heap, like by creating objects and strings and arrays. You know, we put our stuff there, and you know, we know right where it is. How convenient. So I'm not really sure on the class data sharing thing. They mentioned that in their paper, but I went through the code a little bit in Java, and I'm not sure if it's exactly how they said it in their paper. I'm not really sure. I'm going to look at it some more, but it seems to be at least related in some way. And this feature, class data sharing, is Java. At some point along the way, I think in 1.5 somewhere, they decided that rather than JITting and doing all kinds of other stuff every time they started up Java, I guess Java was too slow to start, kind of like Metasploit. But so they decided that they were going to take a whole bunch, like the Java object heap, and just, not actually the Java object heap, but a different area of memory that had all kinds of pointers and stuff, and they just save it off to disk in this file, and then every time they start, they just map that file into memory. So that's really convenient, but it creates this situation that's not good. Does anybody have any questions about what I said so far?
Does the heap manager have it, or does the virtual update have actual managers? Does manager header?
I'm not sure about the metadata in that heap itself. I imagine it does have some in-band management stuff. So that was the question, was there any in-band management stuff in the Java object heap, right? Yeah. I haven't looked at it really deeply at this point. I mean, with the RWX, you don't really care that much, and it's at an address already that you know, and you know you control stuff there. So, and you can make your stuff really big. Yeah, well, I mean, for that you'd need like, he said he's wondering about exploiting the actual metadata in the manager, but the problem there is like they're Java objects, so you'd hope that they didn't screw that up, right? Like, oh, I'm going to create an array that's 4 billion elements. You know, they should be raising a Java exception at that point, going like, you shouldn't do this. But so that would be a vuln by itself if that happened. Anybody else? It's okay. So I'll go on to the hurdles. So the first hurdle that I ran into when I was trying to dev some Java exploits was that there was this interesting issue where you can't really debug the JVM very well, right? If you attach to the process, now that it's external, and you kind of like sit there, and then you continue after a while. If you just wait a little while and continue, or you know, if you're single stepping, trying to understand the code that you're triggering or whatever, then you go at some point, and it doesn't matter if you pass exception or not from the single step exception. It's kind of spurious exception, but if you pass it, then all of a sudden the process just exits, and you're like, what the hell? How am I going to get around this? So, surprise, haha. So why does it happen? So they have a watchdog that watches over the external process, and basically I think they do some IPC and say, hey, are you alive? And then if it doesn't answer, then it just says, goodbye. You can see here's the function inside Java DLL. I have a little screenshot. This process isn't actually this function isn't actually the function that does the pinging or the watching, but this is what is eventually called to kill the external process. So in order to get around it, you just prevent this from interfering at all. You can be really fast if you want. Like if you want to create a debugger script and then just you have your debugger script do what you need, attach and run it real fast and let it run and do its thing. Or just you get in there and you're like single step, single step, single step, single step, go, and then or like breakpoint on the next session, go or something. If you're really fast and you just let it run for that brief window when it needs to do the ping, then you can get around it that way too. But I don't like that way. So what I did for permanency usually is I just patch up the DLL. I'll just go in and knock out the call altogether because I'm like, why does Java need to terminate processes? I don't need any. I like my processes. I don't trust Java to pick which ones. Or you can just change the JNZ to a jump like old school cracking style and just say, no terminate process. And you can do it runtime too. Here's a screenshot here of me like putting a breakpoint in IDA debugger. And if you look at the condition in the breakpoint, it just says, basically set EIP down below where the terminate process is. And this gets rid of it. I mean, Java kind of gets a little confused given that it just killed a process. It thinks it killed the process, but it didn't. But it also thinks that that process is gone, so it doesn't really care. It won't ping it anymore, that's for sure. So another hurdle that I ran into was you'll be debugging and things will be happening, and then you'll just get these weird ass exceptions, and you're like, what's going on here? And it's not like they're a lot of times in programs like Adobe Reader or other programs, you'll get like C++ exceptions, like exception code 40683B2 or something like that. But these are access violations. They're not like just weird C++ exceptions. So you can't just say, ignore all access violations, because then you're not going to find the crash that you're trying to trigger. So I'm not really sure why this happens, but there's some speculation. I have some ideas. Does anyone have any ideas why? Does anyone know why? Damn. So one of the ideas is that like when it jits some functions, it may like say, oh, well, we're going to catch all exceptions while we're in the jitted function in case like we really suck and we screwed up jitting. Maybe. Or maybe they're like using it as some sort of awesome optimization where they're instead of like branching, they're going to do like, we're going to branch by exception or something. I'm not sure. But anyway, one day we'll figure it out, I guess. So these, I just pass them on. I'm like, I don't want this exception. Maybe they want it. Usually the Java lives through it. Sometimes it doesn't. So another problem with Java is they use UTF-8 encoding for basically all strings. So whenever you have a string in your applet or application, it will take that, treat it as UTF-8, and then rather than just like, try to process it UTF-8 and say, oh, well, it failed or something, they'll actually go through and replace all invalid characters with question marks, or they may translate the character into some other character. So, for example, you'll see in the demo, well, actually, I didn't finish that demo. So you'll see, I'll show you guys anyway. There's, like, if you put dead beef into a string, it ends up turning into some garbly mess that looks nothing like dead beef. Well, a little bit like dead beef, but it's not dead beef. So you can't really just shove dead beef into a string, unfortunately. So there's not really great ways around this, but I'll get to that in a sec. This is something from Michael's, I think, does anybody know how to pronounce his name? Shirol or something? His handle's Mihi. He's the guy who wrote the Java interpreter and for Mesbel 8 and a few other Java payloads. And awesome guy. Can't convince him to like security as work, though. So he made this awesome example. It's called OMGWTF. And you can see it looks like a main function with a big-ass block of comments in it. So when you run it and compile it, then it prints out how. What? Did you think Sun printed that out just because there was comments? Well, it turns out that Sun actually made it so that those escape sequences, we'll go back and look at it again, those get evaluated when you compile, like a preprocessor. So what it ends up looking like, they have actually have a command that you can run to like convert it, do the preprocessing. This is what it comes out looking like. So you can see, oh, hey, I'll just close the comment, and then I'll just go ahead and print out this how, which could be anything, right? Like an exploit. But I thought that was really cute, and I know it's not really too on topic, but this is just showing you how sort of archaic and convoluted Java can be. And you could obfuscate your source with it, but in the end, exploits don't go out in source form. So one thing to get around the encoding issues that I've seen is to use like integer arrays. They end up getting represented in memory like just in a sequence of D words, just like they would in a regular C array. So that actually works out pretty well. But there's still an issue with that. The problem is in Java, all integers are signed. There's no such thing as an unsigned integer. So you cannot represent like the value 255 in a byte. You cannot represent 65535 in a short. But there's an easy way around this most of the time. You just use the next larger type. It becomes more of an issue when you have a long and you want to represent like 4 billion in it. But there's ways around that too. I've noticed that if you use hexadecimal notation, then they somehow magically decide that they're going to make it negative for you, which is convenient. So another hurdle is a lot of times some of the Java vulns that come out, like I said, they don't have much information, but they may look like they're not exploitable or reachable in any way when you first look at them. And 2009 3869 CE is actually one of those cases. And it turns out that you can reach these pieces of native code by like doing all kinds of tricks like subclassing. In some cases, reflection has led to some interesting things. And you can abuse things like there are some classes that are abstracted to take like a parameter that's some other class, and then in an applet something will happen with that later that isn't really directly controlled by you, but you can control the argument. And so you set things up where you've got one class and you created it and you pass it into another class, and then sometime later it calls a member function. So anyone questions on that stuff? I'm looking at you, Tony. Oh, okay. Oh, how much time do we have? Oh, we have 15 minutes. All right. So I did some contrived examples, just created some primitives within a JNI module, and I'll explain. JNI module is like Java native interface, and that's Java's way of telling you, like, you can go ahead and make a DLL. You have to use their header files and compile it, and use. You have to declare native methods in Java, and you just kind of put the native keyword in the declaration. You don't put any code in the Java code itself, the Java source file. So I just created these with arbitrary call, write for, and sprnf, and the sprnf is an sprnf into the heap. So then I played with those for a little while. Obviously, arbitrary call is pretty interesting because these type of bugs sadly still happen, and they're pretty convenient. The code just kind of looks like that, and then nice thing about Java, still not supporting ASLR. ROP chains out there. You just kind of jump to the ROP, or whatever you want. So it doesn't support dep either. So that means all the DLLs that you loaded into memory, they have data sections and they have imports and all this stuff. And when there's no dep, those are all executable. So not only, you don't have to stick your ROP only in executable sections. You can use the ROP from like the data segment. Or if you're able to figure out a way through some Java code or a native interface library or something that's already loaded to get your stuff into like a global buffer, that's going to be at a static address and it's going to be executable. So those types of memory priming techniques can make very reliable exploits. And still the latest version, remember? The latest version. So here's the sprnf implementation. It's pretty simple. Can anybody see the bug or bugs in this besides the stack buffer overflow? No? Okay. Well, again, there's two. So there's these two CWEs right there, all in one line. So format string was one of them, and unfortunately, Java's C runtime has the %n disabled, which is pretty common on the Windows platform. It really breaks my heart because I really love format strings, but %n's dangerous. So, but it can still be useful if they have a format string bug, particularly this one here, because there is a buffer overflow. Say there was like a check right before the sprnf that's like if the string length is longer than like 5 or 10 or something, then you obviously couldn't trigger a buffer overflow with a long string. But you could do something like what I have here, where you say, %124x, 1024x, which is going to make a whole bunch of spaces, fill it up, and then you just put these A's and B's, which will hit the return address. You can still leak memory with format strings, which are very convenient. We don't have ASLR in depth, so it's not really that big a deal, but it can still make things more reliable sometimes. So the other one there was the stack buffer overflow, and I won't rant about this. So again, with the UTF-8 stuff can really make these tricky to exploit because you can't really get all the bytes you want usually. Especially if you want to put your shell code like right in the stack buffer. I mean, you can't execute the stack because on modern Windows because the OS itself supports dep, so it won't let you do that. But you can still pad out the buffer and then just put EIP to what you can control, and hopefully you can control it with something that's not going to get mangled UTF-8 style. So some characters aren't usable. These two bugs were both stack buffer overflows. They're fixed in the same patch release, and we'll look at them again in a minute. So with write for, it's more surgical. You have to know where you're writing something. So again, with no ASLR, you just kind of write it wherever you want. And Java has a crap load of function pointers all over the place, and all kinds of really nice stuff like pointers to structures that have function pointers in them, and probably pointers to stuff that will do all kinds of other fun stuff like maybe execute the JIT or something. I'm not sure. So the heap overflow really depends on what you corrupt. I mean, that's kind of the tricky thing with heap overflows, like Tony was talking about. Metadata is usually targeted, but it could be a function pointer. Who knows? It depends on the layout of the heap. So again, unlikely to overflow Java object heap unless there's a serious problem there, but it is interesting. The native protections make these kind of a pain in the butt, so I didn't really look too deep into these. I don't have any POCs for anything like this. So 2009-3867 was a bug that affects these versions. It was in a native sound library that was called through several other Java interfaces and eventually just did a silly string copy. So KF from Digital Munition, he put out a POC that showed cross-platform control of EIP or whatever the program control register is. So I took and made the Metasploit version from his, and it instead of putting like a payload, so he didn't have a payload in his at all because it was just EIP control. But I ran up against the idea like if you want to have a Java applet, that has a payload for each OS depending on which one you're targeting in the Metasploit module, how do you get the payload into the applet? And so what I did was I passed these two variables NP and SC, and that's just knobs and shellcode. So this way you can just pass a few hex ASCII encoded bytes to say this is an APA for this target architecture, and this is the shellcode for that architecture. It worked out pretty well. So this exploit actually sprays the Java object heap. I think it does like 20 megs or something. And since it was before update 16, since it was before update 18, it's still RWX. So I just overwrite it and then jump straight there. It's pretty easy to exploit. Thank you, Sun. Oracle. So the other one is very similar. Like I said, it was released at the same time. This is the native method. I'm not sure. You guys can read that, right? So this thing was called from image representation.setPixels, but this was a class in Sun AWT, and Sun AWT can't be used in untrusted applets at all. They're like, sun.anything, can't call it, I guess because it's not good code or something. Maybe they don't trust their own stuff. So if you try, you get this awesome error message, access denied. So, but the thing is, you can use an image filter class, and it's a similar, the way it works is when you have an applet, you can create a filter that will take an image that you've loaded and do something to it, and then give you back another image that's been mangled. And you can't get to it directly because that's in Sun AWT too, but you can get to an interface that's in Java AWT that calls into this stuff in Sun AWT. So you can create this image filter and kind of pass it to that API. That API will call into the stuff that you're not allowed to call, and then eventually hit the native method. So this was a neat bug. But at the end of the day, it was the same thing. Spray the Java object heap, jump there. Real nice technique. Does anyone have any questions about that stuff? Anybody want to go home? Well, not till tomorrow. I know you want to go home. You have liquor. You're outside. Okay, great. All right, so I wasn't able to put a ton of demos together, but I have one here prepared. Let's see if I can get it on the screen. I tried to do a second one. I'll show you guys the second one, but I'll tell you about why it doesn't work. I guess we only have 5 minutes left. So actually, maybe I can bring this over here too. No, that's not what I want. I don't like touchpads. Do you guys like touchpads? That's actually really creepy. Did you see that? There was a window there, but you couldn't see it. Can you read it? I think I can make it bigger. Yeah. It's the wrong file. So this is the class that ends up calling my vulnerable methods that I created. This is what it looks like when you declare the actual Java side of the DLL. And you just have it load this. You just load it up, and then that's cool. So here's the POC I was able to put together. I just put some shell code in this wonderful integer array. Just runs calc. And then I used the write for primitive to write this into an address here, which is an area in the data segment, an unused area in the data segment within java.dll or jvm.dll. I'd say one of those two. But I mean, it's completely predictable. You can pick any DLL that's from Oracle, and they work. And then I just simply set EIP to it using the arbitrary call primitive that I created. I know it's not much of an exploit, and I'm kind of disappointed in it, but, you know, it's cool. I made this in 5 minutes at the bar. On Thursday. So, I mean, you get calc every time. Want some more calcs? Yeah, well, two's enough, right? So that one's kind of weak, I know. I'm sorry. Let's see where the slides go. Here, let me see. I'll get the other one that I was working on. We were working on one in the ready room, but it got a little tricky on us. So I was working on one for the stack-based buffer overflow. Oh no! Somebody deleted it. Maybe it's in here, the not working area. The folder with the broken demos. So, say again. Why is what?
Why is that 124?
124? I can't hardly hear you.
Why is that folder so much fuller than the other?
Oh, why is it bigger? Why are there more files in the other folder? Yeah. Some of them are not really demos. They were let's see. So like this class here and this one here, they were just, I was using these to figure out which version of Java like introduced the non-RWX heap, which is, I'll release the tool later with the code. But like I managed to make this VM over here, and I have every version of, okay, we don't need Outlook, I apologize for that. Actually, Outlook is a massive fail right now. Okay. Nice. Well, I'll come back to that in a moment. So obviously the format string one is just not going to do anything. Just exits the process. The heap one take too long, and the arbitrary call one is started on. But so the BOF stack one, the buffer overflow stack buffer overflow one, I was trying to just spray the heap like I did before in the 6U16 exploits, and then the plan was to put a ROP in the heap spray, and then use the stack buffer overflow to overwrite the return address, or actually the SEH handler, and then end up in the ROP. But the problem was that we were having issues with the UTF-8 representation, causing mangling in the ROP, and actually you can't have the null bytes in there either. So we weren't able to pull a ROP together in the hour between the last talk and this one. So this is as far as we got. Yeah. So I think I have a couple more slides here. Let's see. All right. So in conclusion, JRE6 can be a pain in the ass. You can see all the wonderful ways they've tried to make our lives more interesting and to make us, not have an easy time. But it's easier than it should be. It's way easier than it should be. In fact, with that DLL from Java, since it's loaded in the browser, you can use it to exploit any vuln in the browser, because it still doesn't support dependent SLR for that module, and it's there. So it's got a big attack surface. It's really buggy. So check them out, the examples when I put them out. I'll make some more demos before I release them, or maybe release them staggered or something. So the recommendations, the good things you can do, you could use EMET to force ASLR in depth. Interesting thing is that doesn't actually affect that wonderfully static memory segment. Stays right there. You could prepare for JRE7 when they fix the loop optimization bug. Or you could use a 64-bit browser and plugin, which they introduced in update 15, I think. As far as I know, there are no malicious code packs out there targeting any 64-bit browsers or plugins. So these things are good. They're good. Better, you can disable the Java browser plugins altogether. You have to install Java and then disable the plugins. And then when you get a new version of Java, you have to go back and disable the plugins again. Well, no, I guess you don't because it's a browser setting. But still, this is what I recommend. Chrome does it by default now. They'll make you click a couple of things before you end up getting owned. So my best recommendation though is just not to install it. I really have no reason to use it except for crashing the shit out of it, or writing exploits for bugs or whatever. I'm not sure what this link goes to anymore. Oh, okay. So this link goes to a wonderful page by some guys who collected together all the reasons to hate Java. It's about 5 pages. One thing, I think bindiff still requires Java, so I think I install Java, use bindiff, and then uninstall Java every time. I think I have a batch file that does it, which I'll release the batch file too. So future things, something I always wanted to do is kind of try to map Java code constructs into native land. So when you create a static variable in Java, does it get put in the Java heap, or does it get put in like a global variable, or like where does that fit into like native memory layout? How does scope translate, or like local variables, are they stored in the Java object heap and garbage collected, or are they like on the stack, or what are they doing? I want to look more into JIT spraying because the JIT is the only address range in the process that is still RWX to this day. It's pretty common. They don't like to remap their pages read-write after they put JIT code in there because it just adds a lot of overhead. And I also would like to look at JRE7 some more. And it does opt into ASLR in depth on all of its modules. They switch to the 2010 compiler. But does it really help? I mean, what about that memory segment that's always in the same place? Is it still in the same place? I think it is. So that's all I have for today. Any more questions? I think they want to kick us out. So one of the things that